All right, hello everybody. My name is Gandhi, and I will introduce you guys to genetic algorithms. So what is a genetic algorithm? A genetic algorithm is a method for solving both constrained and unconstrained optimization problems based on a natural selection process that mimics biological evolution. The algorithm repeatedly modifies a population of individual solutions. At each step, the genetic algorithm randomly selects individuals from the current population and uses them as parents to produce children for the next generation. Over successive generations, the population evolves towards an optimal solution. What is it good for? Well, genetic algorithms are one of the best ways to solve a problem when very little is actually known. It's a very general algorithm and works in almost any search space. All you need to know is, you need basically to be able to converge into what you consider a good solution to be. So it'll make more sense when I go into a couple of examples. And they also tend to thrive in environments where there's a very large set of candidate solutions, a lot of times almost infinitely large, and in which a search space is uneven and has many hills and valleys. Again, I'll explain that as we go into an example or two. And also, genetic algorithms are often good when you're not looking for the best solution, but you're looking for a good enough solution. And in many cases in the real world, that's actually very applicable, where you don't actually care if you got the absolute best, but you want something that's solid enough, good enough for your use case. So it basically goes kind of like this, and the algorithm actually follows these steps very closely, where there's a natural selection, the population, there's chromosomes, which you could judge how good a particular chromosome is based on your fitness function or your score function, which depends on where it is you're trying to go. A crossover, which is kind of like just parents having children, and then mutation, which we typically mimic in a random way. So generally when you have the children or the offspring, with some probability, you'll apply certain mutations to them, which I guess kind of mimics the real world as well. So just to summarize that a little bit, the steps in a genetic algorithm: you generate a random population of chromosomes, you evaluate the fitness, or equivalently the score, which is the function you kind of define in which you judge how good or how bad a given solution is. Then the next step would be to procreate. And there's various ways to do it. The traditional way, you'll select two parent chromosomes, and typically you have some sort of functionality. So if you have a population of, let's say, n chromosomes, you would choose two of them randomly, but with some sort of distribution, so that the ones that are more fit or better, closer to the optimal solution, will be more likely to be selected. In my examples, I kind of modified it. I'll go into it a little bit, but this is the traditional way you would go about doing that. Then the crossover stage, you basically have parents and they produce offspring. What does that mean? Well, you could define it in your own way, but you kind of want to take the two chromosomes and in some way merge them together in something that, there'll be some level of randomness in that. One thing you do if you have two chromosomes, you can say, hey, the first half comes from one parent, the second half comes from the other. In one of the examples I'll do, you can't quite do that because there's other restrictions. But typically you want to come up with some manner that you're mixing two parents to create a child or many children. And then a mutation. And like I said before, typically you have a mutation probability, and you randomly at a given position mutate a child or apply a mutation to a potential child. And finally, as brutal as it is, you kill off anyone who's unfit. So you're like, hey, out of this population of potentially infinitely many combinations, we're only going to keep the top 10 or the top 100 or the top 1,000, and the rest, they basically stop procreating, so they die off because they're no longer fit to procreate, because they're nowhere near optimal. They're not leading towards anything that you consider optimal. Right. So now you might be wondering, what's the reason for a mutation? The big issue is very often you'll end up running into situations where you're hitting a local optimum. If you're really trying to get into honing in on, hey, this solution is getting closer and closer and closer because my score function is getting better and better. Score is usually inverse, so lower and lower. You're getting very close to a ideal solution. But at some point you'll notice you're never actually getting there because you're stuck on a local optimum as shown here. And often, for lack of a better way of describing it, it's because your chromosome, it's kind of incestual. All the chromosomes are coming from the same parent or the same great-grandparent, and they're kind of intertwining, and it's very incestual. And maybe there's a certain part of it which you need help from a completely different entity that's completely unaffiliated with you, your grandparent, all of that, to actually make that jump. Which, now I'll go into a couple of examples. The traditional intro example is a hello world example, where, let me see what I have here. All right, so I'll go through it twice in two different ways. The first way, I was like, you know what, let's forget about having parents. Let's just say you started with one normal chromosome, which is a completely randomly generated string, which happens to the same length as hello world. And from there, so this is, again, not traditional genetic algorithms, but we're like, hey, we'll just mutate it and print out the next generation just off of one. So no, not including parents. And so what I did here, basically I evaluated a score. I gave it a score function, which kind of judges the distance of this completely random string from hello world. Then through each iteration, we mutate it. And the mutation is, again, random. So I take this random string we selected, pick a random point, a random letter or character within the string, and mutate it to something completely different at random. So this is the whole point is it's completely random. And I'm going to show you how a completely random string, along with a score function and genetic algorithm, will generate hello world. So, whoops. So we'll just run this main function, and you can kind of see. And so the first number here shows you generation. So the random string that was generated is this thing that starts with G/ so on and so forth, completely random string. In the next generation, it mutated a little bit and got something a little bit better. But the score function, which is the second item, is still very far from 0. In our case here, we want a score function to be 0 when it matches and it's basically overlapping exactly with hello world. So as you can see, you get closer and closer. Right now, it still looks very foreign. As you scroll down, you notice you're kind of getting closer, closer, closer. And usually, and in this case it did, it actually terminated into hello world. And that's through, it took 4,849 generations, but eventually we got to hello world based on this score functionality. So that's the case without the parents. So in the proper way to, or not the proper, a different way to do it is with the parents, where again you have the same score function to judge how far you are from hello world. The mutation function is still the same, but now we have this whole half-child business going on here, in which you basically, from this population, so sorry, in this case instead of starting with 1, I generated a random set in the population, which in my case I had set to 20. So still the target is hello world. You can change that to whatever you want. The longer the string is going to be, in theory, it should take more iterations to get there. So then I set a population of 20 random strings and basically did the exact same process, except now we have a have-child function, which will choose 2 parents, or given 2 parents rather. It generates a child. And what I did a little differently here, instead of just saying, hey, there's a random mutation, and normally they say, hey, with certain probability M or P, you mutate the child. What I did was I actually ran through all kinds of possible mutations and just took the most fit mutation. So in other words, all the mutations that might go bad, I dumped instantly. And if a child is better off being mutated, I mutated it before even throwing it into the pool. Although if the child itself was better than one of the previous parents, I got rid of the parent and kind of just kept the child. But those are just details. And again, you could do it in many different ways. But the basic idea is having the score functionality, having a way to judge, and kind of taking it from there. So in this case, which is in a separate file, main2, if we run it, you notice in 95 generations versus whatever it was, a couple of thousand, you actually end up with the same thing. And now things kind of happen a lot faster. You notice very quickly you're kind of getting closer and closer to hello world, which here in 95 generation, in the 95th generation, you hit hello world, and that has a score of 0. And I guess the one thing I didn't explicitly state, you need to know when you're going to terminate this whole process. In this case, it's easy because hello world is something we know we could actually reach because we know what the end goal is. So I terminated it when the score actually hits 0. But in a case where you're looking for a good enough solution versus the best solution, and remember, genetic algorithms is really good for a situation where you don't know what the best solution is, and it might be a solution which you can't realistically get to. You want a way to know, hey, when do I stop this? When is it no longer worth going through more iterations? And there's several ways you could look at it. In one case, you could say, hey, if my score function is below a certain point, so I don't know if I could hit 0, but once it's like 10 or 100 or whatever arbitrary amount, you could stop then. Another case, you could say, hey, if I'm iterating and going generation by generation, if I see no improvement after, I don't know, 100 generations, then maybe I should stop. Or 1,000 generations, again, that's kind of arbitrary. Or you could say, not only do I not see, maybe in the ideal case, or in one case, you see 0 improvement. In other cases, you could say, hey, the improvement after 100 generations is so negligible that I'm satisfied with the solution I have. I don't really want to necessarily go further. And that kind of leads to the next problem I'll talk about, which we discussed, if you remember, first week, was a traveling salesman problem, which could be stated in a simplified manner. It can be stated as, it describes a salesman who must travel between n cities. The order in which he does so is something he does not care about, as long as he visits each one during his trip. Each city is connected to other cities or nodes. Each of those links between the cities has a weight or a cost attached to it. The salesman wants to keep the distance or some function of the distance he travels as low as possible. So a brute force solution for this, if you have n cities, there's n minus 1 factorial possible combinations of orderings of how you could go hopping from one city to the next. And if n is 10, you're already above 180,000. If n is 20, it's enormous and would take an extremely long time to actually compute. And I guess if n is like 30 or 40, I don't know what the latest computers, how fast they go, that's going to take several lifetimes to actually compute if you're going through every one by brute force. So that concept is actually so the traveling salesman is an example of an NP-complete problem, which means with extremely high certainty, there's no polynomial time algorithm to solve this problem. And P equals NP, that's actually an unsolved math problem. It's one of the 7 Millennium Prize problems selected by Clay Institute, I believe in 2000, and it came with a $1 million cash prize. It has not been solved to date. And to go into what that means, a P problem is a problem that's fast for a computer to solve. And it's considered an easy problem. An NP problem is a problem that's fast for a computer to check, but it's not necessarily easy to solve. And they still don't know. So the question is actually asking, is P equal to NP? And once again, in layman's terms, the question is asked, can every solved problem whose answer can be checked quickly by a computer also be solved quickly by a computer? And it's very widely believed that the answer is no. And a little corollary to that is, if you could prove that this is false and it actually is possible, then that carries over for every NP problem. There's tons and tons of classes of problems in computer science that are considered NP hard. And if any one of them can be solved, in essence, absolutely all of them are solved. So that's why this problem here is actually really valuable. They're offering a $1 million cash prize, since it'll actually change a lot that goes on in computer science and the algorithms if you solve any one of those problems. But in essence, they're all the same. So this is an example of a situation where a genetic algorithm might come into play. Because, in the real world, if you're looking for traveling salesmen, I don't know, maybe like a UPS or FedEx driver, he has to make 10 stops. How do you decide what's the optimal path? Well, you don't really care if it's the best, right? The UPS guy's going to go one way or the other. He's not going to sit there all day for 10 years or 100 years saying, hey, was that the best route for that one day? He just wants to know, hey, what's kind of the best thing I could do today? I have no clue if that's what they actually use, but that's one thing I would think that one can use. So I kind of did the same thing, and it's kind of the exact same setup. Where here, so right now I hard-coded a city, but really I have this line over here which generates a random city. But just for the examples, I'll use the hard-coded city. So I said, okay, fine. If you have 20 cities, how can you find the optimal path between them? And again, I generated a population of potential paths. And the way I did it, I just said, okay, fine. You have 20 cities numbered 0 through 19. And you could just randomly select or randomly create a shuffle of that array as your population. You can create as many as you want. Let's say I created 100 in this case for the initial population. And at the same time, you could have a score function, which I have here, which is just, it computes the total distance you're traveling. And again, this could be different. Like if you're actually thinking about real cities versus like little houses in a small city, you might add into situation the cost of the airplanes, this and that, whether you're taking other modes of transportation. So it doesn't have to be purely distance. You could modify the score function accordingly, depending on what it is that you actually care about. But the score function is essentially set up just taking the sum of the distances, generating a random path, and just a couple of helper functions there. I have this cool shuffle function. And in this case, I'll do it with a hard-coded city. But right now, the hard-coded city has length 20. For demonstration first, let me just chop it down to like, I don't know, what is that, like 14, 15? Let me just comment this out. And then we'll go to all 20 cities afterwards. So in this case, if we run this now, it's going through each iteration, and that's the actual array. It started with 5, so start in steady 5, go to 10, go to 4, so on and so forth. And the sum of the distances comes out to 544.48. That's the initial. Then it goes to this whole mutation stage. The second iteration goes to this, gets 403, then 350, 328, and 324. And kind of seems to be terminating there. It's still running, trying to see if it finds anything optimal, but it seems like it terminated. I actually have it checking if after 100 generations nothing happens, terminate, but most of the time, for reasons I'll get into in a few seconds, it tends to terminate very quickly. Only once or twice I saw where after it stops at like a certain point, it would take many, many, many generations before it breaks out. And again, that actually goes into what I believe is probably the whole incestual case, where the top X number of solutions I'm keeping are very similar. Maybe they all start with like 1, 13, 2, 0, and the actual optimal solution might be completely different, where it would take a ton of extremely random mutation to break out of it. Because remember, you have the parents, they combine together to give you ideas of like an optimal path. Maybe the first half is like this, or certain parts of it like that. And then the mutations. If you rely purely on mutation, as you saw in my first case with Hello World, it's like 4,000 generations. Versus if you throw in this whole concept of, hey, you actually have 2 different good strings, or 2 different optimal paths, or 2 different sub-paths that are actually pretty good, it gets done much faster. If you rely purely on mutation, it'll take a ridiculous amount of time. So to very quickly go through this is one iteration. If we start with a completely separate random thing, which it looks similar to 544, but it's actually different, it actually went a little lower to 315. And if we go one more time, let's see where it stops. Like I said, two times in a row we got the same answer, so I'm inclined to believe that's good, but there's no guarantees. If we land there 1 or 2 more times, I'd be like, okay, seems like 3 times you got the exact same thing. Now you might look at the bottom line in the second to last versus the last and say, oh, they're actually different. But if you look at it carefully, it's actually just the opposite path. You start with 12, go to 6, 7, 4. Here it's actually the reverse. So really they're the same essential path. And the final thing I'll show you is if you actually do this entire thing instead of with 14 or 15 cities, but you actually run it across the entire array, you might run into a little issue. So in this case, where in the last case, it kind of converged 2 or 3 times, you got 315. In this case, since there's more cities, you're actually much less likely to get the same terminal factor. You might get things that approach the same. They never actually, or it's unlikely it'll terminate at the same point. So right here in this case, we got 376. I don't expect future generations to get better, so I'll just terminate this, and we'll just look at a couple. So we have 376. That's kind of the running best. Now it's 382. So you see they kind of terminate at different points. And it's probably unlikely we'll see the same best point twice. But one thing you could do is you could say, hey, those last ending terminating points are actually good fits. So what you could do is, hey, create a population. Run this 20 times. Create a population of the 20 best fits, which are probably very different. And on that, you might actually end up getting things that are even better. All right, so that's my introduction. Hope you guys learned a thing or two. And perhaps you'll find applications in real life where you could apply this.